about one important concept that is delta to star conversion and star to delta conversion. After that, you have to see what is the concept of open circuits and short circuits in a series connected networks and parallel connected networks. Then you will solve some practice questions based on star to delta, delta to star conversions. Then we will see some practice questions with respect to connection of the elements. First, we will start with the delta to star conversion, that is delta star transformation. To simplify the circuits, how to convert delta to star and how to convert star to delta, that knowledge is very important, students. First, I am going to explaining delta to star conversion. Delta to star conversions. That you have to concentrate. In delta to star conversion, let the impedances in delta connection, you have to assume like this. In delta connection, you have to consider the impedances are ZA, ZB, ZC. This I am taking ZA, ZB, ZC. The impedances in star connection is, let this is Z1, let this is Z2, and this is Z3. We are converting delta to star. Remember like this, friends. Delta to star conversion means we are calculating the impedances with respect to star connection. Then how to calculate Z1? Simply remember like this. If you have to calculate this impedance in star connection, multiply this opposite. This is ZA into ZC. That is ZA ZC by sum of all the impedances in delta connection. That is ZA plus ZB plus ZC. How to apply delta to star conversion? That mainly you have to concentrate. No need to by heart the formula. You have to calculate this impedance. Take product of opposite this. That is ZA into ZC by total impedance ZA plus ZB plus ZC. First, I am explaining with respect to impedances. Then same formulas you have to apply for resistor, inductor, and capacitor also. Replace impedances by resistor, inductor, and capacitance. You know that impedance and capacitance is exactly inversely proportional. That you see even in the series and parallel connection of elements also. Then how to calculate that? This is Z1 students. This is the impedance in star connection. Then what is Z2? If you have to calculate the Z2, product of opposite ZA into ZB, ZA ZB by the total impedance ZA plus ZB plus ZC. Okay, this is the Z2 calculation of impedances in star connection. Then how to calculate Z3 students? If you have to calculate this Z3 impedance, product of opposite the ZB into ZC, ZB into ZC by ZA plus ZB plus ZC. These are the impedances calculation. Now you have to calculate, replace these impedances by resistive element, inductive element, and capacitive element. Now applying that formulas for resistance. The first one is for resistance. For resistance, you know that for resistance you have to replace Z equal to R. For resistance, the impedance equal to resistance. Then how to calculate R1? Instead of Z1, I'm taking R1. Then RA into RC, like this. RA into RC by RA plus RB plus RC. This is a calculation of R1. Then how to calculate R2? R2 equal to this one. Instead of Z2, I'm taking R2. RA into RB by this one. RA into RB by, that is RA plus RB plus RC. Now to calculate R3. Then what is R3? ZB ZC RB into RC by RA plus RB plus RC. This is for resistance. Next, second one is for inductance. for inductance. Students, we know that for inductance, you have to replace Z equal to J omega L. Numerator also J omega L, denominator also numerator also J omega, denominator also J omega. Then J omega cancel. Then directly I'm calculating L1. Directly I'm writing L1. Students, L1 equal to, same. The inductance formulas are similar to resistance formulas only. That is LA into LC by LA plus LB plus LC. Then how to calculate L2? L2 equal to LA into LB by, how to write? That is LA into LB by LA plus LB plus LC. Similarly, how to calculate L3? L3 equal to LB into LC by, that is LA plus LB plus LC. This is for inductance. The last one is how to calculate for capacitance. Third one is for capacitance. If the element is capacitance, how to apply delta to star conversion for capacitance. We know that for capacitance, how to write impedance equal to Z equal to 1 by J omega C. Then if you write 1 by J omega C, then how to calculate C1? C1 equal to 1 by CA, 1 by CC by 1 by CA plus 1 by CB plus 1 by CC. Like this I can apply. Clear, students? Just replace the impedance. If it is a capacitance, directly the capacitance is given. Like this we have the delta to star. What is C2 equal to? 1 by CA, 1 by CB. Yes, students, by, I'm calculating the C2. Calculating C2. And this is the C1 calculation. How to apply like this? So this is the C1 calculation. That is 1 by CA plus 1 by CB plus 1 by CC. How to calculate C3 equal to 1 by CB into 1 by CC by 1 by CA plus 1 by CB plus 1 by CC. This delta to star conversion formulas for resistance, inductance, and capacitance. One observation here, friends. Note point I'm giving. If you take R, that is RA equal to RB equal to R. If RA equal to RB equal to RC equal to R, that is, if all the resistances are equal in delta connection, then what is the resistances in star connection? This is for delta. For delta. Then what is for star? For star, substitute this is R square by 3R, R cancel, that is R by 3. Similarly, if LA equal to LB equal to LC equal to L, this is in delta connection, then what is L1 equal to L2 equal to L3 equal to, that is L by 3. That is in delta to star conversion. In star, the resistance is reduced by 1 by 3 times and inductance also becomes 1 by 3 times. But what are the capacitance? If CA equal to CB equal to CC equal to C, then what is C1 equal to C2 equal to C3 equal to 3C? It becomes 3 times. That is in delta to star conversion. In delta to star conversion, resistance and inductance reduced by 3 times, but capacitance is increased by 3 times. This note point I am giving, students. This note point you have to write here. This I am writing. Therefore, in delta to star conversion, R and L reduced by 3 times. Reduced by 3 times. But C increased by 3 times. Increased by 3 times. It is better I will write in the next ending slide. Next slide. That is better. Here not appearing. This note point I am giving, students. In delta to star conversion, R and L reduced by 3 times. Reduced by 3 times. Reduced by 3 times. But C increased by 3 times. 3 times. But capacitance is becomes 3 times. That is in delta to star conversion. The next concept is you have to see star delta transformations. Star to delta conversion. That is star to delta conversions. First, I am explaining for impedances. Then directly you can apply these formulas for resistor, inductor, and capacitor. Let in delta connection, the impedances are ZA, ZB, ZC. So this is ZA, this is ZB, and this is ZC. In star connection, the impedances are Z1, Z2, Z3. In star to delta conversion, you have to calculate delta impedances. How to calculate delta impedance. See, for example, how to calculate ZA. How to calculate ZA. It's very simple. No need of any derivation. If you have to calculate ZA, multiply all these impedance Z1 into Z2, Z2 into Z3, Z3 into Z1. Like this, you have to write Z1, Z2 plus Z2, Z3 plus Z3, Z1 by, you take for ZA opposite is Z3. You take Z3. You can also write this formula like this. Divide with Z3. Then Z1, Z2 by Z3 by plus Z2 plus Z3. Z3, Z3 cancel. Z1, Z2 plus Z1. That is, if you have to calculate this ZA, one method is product Z1, Z2 plus Z2, Z3 plus Z3, Z1 by ZA opposite Z3 divide with Z3. Or otherwise, if you have to calculate this ZA, Z1 plus Z2, these two you have to add and multiply these two and divide with Z3. That is one more way to remember. Add these two plus multiply these two and divide by this. That is Z1 plus Z2, Z1, Z2 by Z3. Understand, students? If you want to calculate ZA, this is one way to remember. The another way is Z1 plus Z2 plus Z1, Z2 by Z3. Next, how to calculate ZB? Same procedure. Z1, Z2 plus Z2, Z3 plus Z3, Z1 by, for you are calculating ZB now. For ZB opposite is which one? Z1. Divide with Z1. Or you can also write like this. If you have to calculate the ZB, these two products Z2, Z3 by opposite is Z1 divided by Z1 plus add these two Z2 plus Z3. Just we are dividing with Z1, we can get this. Next, last one is ZC. Yes, same procedure you have to apply for ZC. Then how to calculate ZC? Z1, Z2 plus Z2, Z3 plus Z3, Z1 by, for ZC which is the opposite, Z2 is the opposite. Or you can also write ZC equal to, multiply these two. If you want to calculate ZC, Z1, Z3 by opposite is Z2 and add these two plus Z1 plus Z3. This is another way to remember. Yeah, this is ZA formula, this is ZB formula, and this is ZC formula. This is the ZC formula. Like this you have, this is ZA calculation. Any way to remember either this formula or this formula. And this is the ZB formula. And you have to remember this as a Z3 formula. So ZC formula. ZA, ZB, ZC. Now we have to apply this formula for resistors, inductors, and capacitors. That is star to delta conversion. First I am applying for resistors. For resistance. For resistance, how to calculate RA? You have to replace Z equal to R. How to calculate RA? That is R1, R2 plus R2, R3 plus R3, R1 by RA. By which one? By R3. You can also simplify this. It is also equal to R1, R2 by R3 plus R2 plus R. Have to add this two. Similarly, calculate RB. R1, R2 plus R2, R3 plus R3, R1 by, just replace Z equal to R by R1. How to simplify this? You can also get, so this is R2, R3 by R1 plus R2 plus R3. Then last one is RC. R1, R2 plus R2 R3 plus R3 R1 by R2. How to write R3 R1 by R2 plus R3 plus R. Just divide with R2. You can get this far. R3 plus R. Okay. This is Z1 Z3 by Z2. R1 R3 by R2 is R1 R3. R3 R1 or R1 R3, whatever. Both are same. You write R1 into R3 or R3 into R plus R3 plus R. This is for resistance. For inductance. Now try the formulas for inductance also. In inductance, Z equal to J omega L. J omega cancel, then L only can get students. How to write LA? Is LA equal to L1 L2 plus L2 L3 plus L3 L1 by R3. This is L. You can also simplify like this. L1 into L2 by L3 plus L1 plus L2. How to calculate LB? L1 L2 plus L2 L3 plus L3 L1 by, for LB how to calculate L1. Here Z1, that's why it is L1. How to simplify this? L2 L3 by L1 plus L2 plus L3. By simplifying this, you can get this. The last one is LC. L1 L2 plus L2 L3 plus L3 L1 by, students, last one is L2. Then you have to simplify this, what you can get? That is L3 L1 or L1 L3. That is L1 L3 by L2 plus L3 plus L1. How to apply? Already explained. Then last one is for capacitance. For capacitance. Here I am applying the star to delta conversion. Star to delta means delta parameters I am calculating. Z equal to 1 by J omega C naught. Then what is CA? Now to apply the formula of CA. Then 1 by C1 C2 same, but inverse you write 1 by C1 C2 plus 1 by C2 C3. This one 1 by C3 C1 by C3 C1 by 1 by C3. What is CB? We want to simplify this also. Same 1 by C1 C2, 1 by C2 C3, 1 by C3 C1 by 1 by C1. Last one CC, how to calculate students? 1 by C1 C2 sir, 1 by C2 C3, 1 by C3 C1 by 1 by C2. Okay, this about for resistance, inductance and capacitance, how to apply star to delta. Now in these cases, if you equate R1 equal to R2 equal to R3 equal to R, we can get RA equal to RB equal to RC equal to 3R. Here LA equal to LB equal to LC equal to 3L. But here CA equal to CB equal to CC by C by 3. That is in star to delta conversion. Resistance and inductances are increased by 3 times, but capacitance is capacitance is reduced by, reduced by 3 times. That is in the above conversion. If R1 equal to R2 equal to R3 equal to R, then you can get RA equal to RB equal to RC equal to 3R. L1 equal to L2 equal to L3 equal to L. LA equal to, yes friends, LB equal to LC equal to 3R. C1 equal to C2 equal to C3 equal to C. Then CA equal to CB equal to CC equal to C by 3. That is in star to delta conversion. That is in star. Therefore, in star to delta conversions, resistance and inductance increased by 3 times. But capacitance is reduced by 3 times. That is in star to delta conversion. But in delta to star conversion, RL reduced by 3 times, but C is increased by 3 times. But here C is reduced by 3 times. This about the concept how to apply star to delta and delta to star transformation. For the concept of star to delta conversion, delta to star conversion. Clear? That you have to concentrate. Can anybody answer this question? If each branch of delta circuit has impedance of root 3Z, then each branch of the equivalent star circuit has impedance of. If each branch of delta circuit has impedance of root 3Z, then each branch of equivalent star circuit. Here what it is given, each branch of delta, that is Z delta equal to root 3Z. Then each branch of equivalent star, Z star. We know that here resistance, inductance, capacitance is not given, simply impedance it is given. That is, we have to convert delta to star. In delta to star conversion, impedance is reduced by 3 times. Impedance is reduced by 3 times. Then Z star equal to Z delta by 3. What is the Z delta? Root 3Z. Root 3 Z by 3. That is root 3 into Z by 3. I am writing root 3 into root 3. This is equal to Z by root 3. Then what is the Z star, friends? The impedance in star connection equal to Z by, that you see in delta to star conversion. In delta to star conversion, this one. You take ZA equal ZB equal ZC. Z square by 3Z, Z cancel, Z by 3 you can. That is if ZA equal to ZB equal to ZC equal to Z. I'm talking about impedance. It's not a resistance inductance. Then what about Z1 equal to Z2 equal to Z3 equal to? This becomes Z by 3. This Z1, Z2, Z3 are the impedances in star connection. Then these are impedances in delta connection. The impedance becomes 1 by 3. That is, I'm dividing with 3 steps. So that you have concept. If you see in, that is in star to delta transformation, if Z1 equal to Z2 equal to Z3 equal to Z, then what is the ZA equal to ZB equal to ZC? It becomes 3Z. Impedances are becomes 3Z. Impedance becomes ZA equal to ZB equal to ZC equal to 3Z. If you want to calculate this, do this. This Z cancel, Z plus Z plus Z, 3Z we get. Clear? Okay, then according to that observation, we are getting Z by 3. Can anybody? Consider a delta connection of resistors and it is equivalent star connection and shown. If all the elements of the delta connections are scaled by a factor of k, the elements of the corresponding star equivalent will be scaled by a factor. This is delta connection and this is the star connection. Okay. See, for example, I'm drawing like this for easy solving. This is the delta connection. This is RA and this is RB and this is RC. This is small letters. This is RA and this is RB and this is RC. And this is the star connection. I am drawing like this. This is the star connection. This is the star connection. Like this is RC and this is RB and this is RE. Calculate any one element. See, for example, I am calculating RA in star connection. This is star connection. How to calculate RA? Product of opposite RB into RC by total RA plus RB plus RC. Here the question is, if all the elements of the delta connection is scaled by factor of k, if all are scaled by factor of k, if all are scaled by factor of k, what is the equivalent scale factor in star connection? This is star connection resistance. Now delta connection, each element is scaling by factor of k. Factor of k. This I am writing. That this is RA dash. This is KRA plus KRB plus KRC. Then what is RA dash? This RA dash equal to, or simply you have to, again no need to take RA dash like that. Let this RA, how much time? So this is RA equal to k into k square by k. Take the k is common. RB into RC by RA plus RB plus RC. Every element is scaling by a factor of k. If every element is scaling by factor of k in delta connection, in star connection, it becomes k. Then what is RA equal to K into, this is K into RB, RC by RA plus RB plus RC. That is, every element in the delta connection is scaling by a factor of K. In star connection, it is scaled by a factor of K. The total impedance, that is, the elements of the corresponding star equivalent will be scaled by a factor of K. It is scaled by a factor of K. That is option B. Small RA, small RBs, that is R small a, R small b, R small c is delta connection. Every element of delta connection is scaling by a factor of K. Then this becomes K times of this total. That is, that RA is scaling by a factor of K, increased by a factor of K, or scaling by a factor of K. That's the meaning. Clear, students? Like this you have to answer. Can anybody answer this question? A star network has a resistance of 10 ohms, each in two of its arms, while third arm has a resistance of 11 ohms in the equivalent network delta. The lowest value among the three resistances. To try this one, students. It's very simple. Try this practice. If you have any doubt, you can share your doubt in my Telegram channel. See the one more question. Can anybody answer this one? This is a GATE E 2004 question, 2 marks question. In figure, RA, RB and RC, 20 ohms, 10 ohms and 10 ohms respectively. The resistances R1, R2 and R3 in ohms and equivalent star connection. You have to calculate equivalent star connection. Yes. Calculate. What is R1? If you want this calculation of R1, RB into, you connect here. Connect here. This is R1 as it is. This is R2. This is R3. What is R1, students? R1 equal product of opposite RB into RC by RA plus RB plus RC. RB into RC. This is RA. This is RB. And this is RC. This value is RB into RC. 10 into 10 by 20 plus 10 plus 10 students. How much you can get? 100 by 40 students. So this is equal to 2.5. How to calculate what is R2? If you want to calculate this R2, RC into RA. This is RA. RC into RA by RA plus RB plus RC. RC into RA, that is 20 into 10 by 20 plus 10 plus 10. This is how much? 200 by 40. This is 5. What is R3? RA into RB by RA plus RB plus RC. That is RA into RB, 20 into 10 by 20 plus 10 plus 10. This also 5 ohms. That is R1, R2, R3 respectively 2.5 ohms, 5 ohms, 5 ohms. Which option is correct, sir? That is option 1 is the right answer. That is 2.5 ohms, 5 ohms, 5 ohms respectively. These are questions based on the star to delta, delta to star conversion. This you try for practice. This question also you have tried to practice. Before starting this, 2 more questions I have to solve here. Just a minute. Whatever I'm giving for practice purpose, please all of you try this. If you have any doubt, please share your doubts in my Telegram channel and I will send the detailed solution. Just for practice purpose, some questions I'm leaving for. Yes, please. So for example, the question is asked like this. Find the delta equivalent for the circuit shown in figure. Find the delta equivalent for the circuit shown in figure. Shown in figure. So this is the given. This is the delta it is given. This is CA. This is CB. And this is CC. CA, CB, CC. And the star capacitances are given like this. This is 2 farad, this is 4 farad, and this is given 6 farad. Can you calculate what is CA, CB, and CC? Can you try this? How to calculate CA? That is, this is a question based on which one? Star to delta conversion. In star to delta conversion, if you have to calculate CA, what is the concept you have to apply? Product of this 1 by 2, 1 by 4, 1 by 2 into 1 by 4 plus 1 by 4 into 1 by 6, 1 by 6 plus 1 by 6 into 1 by 2, 1 by 6 into 1 by 2 by opposite is 4, that is 1 by 4. Calculate this, I am leaving 5. How to calculate CB, students? 1 by 2 into 1 by 4, 1 by 4 into 1 by 6, 1 by 6 into 1 by 2. This value is same for all. CB opposite is 6, that is 1 by 6. Try this. How to calculate CC? Same 1 by 2 into 1 by 4, 1 by 4 into 1 by 6, 1 by 6 into 1 by 2. For C, opposite is 2, that is 1 by 2. Calculate this. Yeah, that is the answer. One more example, students. Can you try this? Here you have to calculate CA, CB, CC, that I am leaving for you. Calculate this. And CB also you calculate, and CC also you calculate. Two more example I am leaving for you. Find the delta equivalent for the circuit shown in figure. Find the delta equivalent for the circuit shown in figure. Find the delta equivalent. How to find delta equivalent for the circuit shown in figure. Shown in figure. How to try it? If it is given like this, is the delta connection. And these are the star impedances it is given. This is inductance, and this is capacitance, and this is the resistance. This is the resistance. This ZA, ZB, ZC it is given. This is ZA, this is ZB, and this is ZC. These impedances are J5 ohms. These values it is given. This is J5 ohms minus J5 ohms. This is 5 ohms. Right. These are impedances. Directly you have to apply for impedance values. Don't take as a capacitor, resistor like that. This is directly given as a impedances. Minus J5 ohms. Then you have to calculate ZA, ZB, ZC. How to apply that formula? Product of all these. J5 into minus J5, or otherwise, if you want ZA, this into this by this, and add this to 5 plus J5. Like that also you have to solve. Yes, friends. Find the star equivalent for the following circuit. This is practice. Find the star equivalent. Find the star equivalent for the following circuit. This is a given delta connection. J3. This capacitance is minus J3. And this again inductance plus J3. This is J3 minus J3 minus J3. And this is plus J. You have to find star equivalence. This is delta to star conversion. This is star to delta, but this is delta to star. These impedances you have to calculate. Let this is Z1, this is Z2, and this is Z3. Calculate Z1, Z2, Z3. Yeah, this is about delta to star conversion, star to delta conversion. That you have to consider. And one more important concept in the fundamentals of electrical circuits is that is source transformations. This knowledge is also very important to solve the different models of questions or to simplify the different circuits also. That is one more concept is that you have to see source transformation technique. Friends, any doubt in the explanation of whatever I given in star to delta and delta to star conversion? So, okay. The source transformations. Since the characteristics of voltage and current sources are dependent on the terminal conditions, it is possible to transform a voltage source into a current source and vice versa. That is, you have to transform a voltage source into current source or current source into voltage source without modifying the response in the network to which it is connected. That is, without affecting the network response, we have to transform voltage source into current source or current source into voltage source. An electrical source transformation or simply source transformation, a method for simplifying circuits by replacing a voltage source with its equivalent current source or a current source with its equivalent voltage source. Why you are going for the source transformations? The reason is to simplify the circuits. That is the only reason. Source transformation are implemented using Thevenin's theorem and Norton's theorem. You'll see in the explanation of theorems also, mainly in Thevenin's theorem, a voltage source in series with resistance. In Norton's theorem, a current source in parallel with resistance. That later on that I will explain. That where also you can apply the source transformation using Thevenin's theorem and Norton's theorem. Source transformation is a technique used to simplify an electric circuit. Is applicable only for practical circuit. We don't apply any source transformation for ideal circuit, ideal current source, ideal voltage source. We have to apply only for the practical circuit. So, for example, let's consider okay, this is the a voltage source. How to apply source transformation? This is plus minus. A voltage source, practically a voltage source having the some series resistance. RS is the series resistance. Vs is the source voltage. Let this current enter into the network is I. For this source, let this is the externally connected network. This network is connected. Network or circuits. Let the terminal voltage is this is V plus minus V. This is the current direction. Okay, this voltage source in series with resistance. If you apply KVL in this loop, friends, apply KVL here. What is the equivalent you can get? Apply KVL. If you apply KVL, this is the current entering. You take plus minus. Positive to negative, negative, minus I into RS. Positive to negative, negative, minus V plus Vs equal to 0. How to take the, that is, polarity that I already given. Then from this, what is V equals, friends? Vs minus I into Rs. This V equal to this total voltage minus drop. That is the meaning. V equal to Vs minus I into Rs. Now, you have to replace this like this. Now we are applying the source transformation. Using source transformation. Using source transformation. How to convert this voltage source into current source? Simply you can do like this. How to get the current Vs by Rs? This voltage by this resistance. Vs by Rs. In current source, in the explanation of practical current source, we know that practically a current source is having a resistance in parallel with the source. You have to connect as a parallel resistance. This is Rs. Using source transformation, this is Rs. Now this current, now it is connected to the network. It is connected to the network. This is the network. Without affecting the the response of the network. Then voltage across this one is V1. This voltage remains constant. Even though you can apply the source transformation, this voltage remains constant. This V remains constant. Yes, I will do the proof also. This voltage remains constant. Now this is V means let this is also V. Let this current is I. I remains constant, V remains constant. Without affecting this, we can apply the source transformation. Without affecting this, we have to apply the source transformation. Say for example, apply KCL at this node. This is entering current, leaving current, leaving current. Entering currents are taken as a, you have to take the negative minus Vs by Rs. Leaving currents you have to take as a positive V by Rs. This current, how you can write V by Rs. This leaving current is plus I equal to 0. Now simplify this one, students. What you can get? Minus, that is minus Vs by Rs. Now, shall I write like this? To simplify this. This Rs is LCM minus Vs plus V plus I into Rs equal to 0. Then from this, V equal to Vs, bring this Vs this side, Vs minus I into Rs. That is finally the V equal to Vs minus I into Rs. This remains same. I'm getting same value. That is the meaning. You have to apply the source transformation in such a way that without affecting the response of the lead. Whatever the voltage we are applying for the network V and current, this remains same. Without affecting that, we can apply the source. Then this and this is same final. The above circuits are equal with respect to performance point of view. But the elements and connection point of view not same. That is, if you analyze the performance of this network, if you analyze the performance of this network, same performance. But in network's elements point of view, connection point of view, it is different. But the elements and connection point of view, it is not same. This RS is connected series, but RS is connected parallel. But this is the voltage source, but this is the current source. That is, in connection point of view and elements point of view, it is different. But performance point of view, these two networks are same. Finally, if you analyze calculate the current, calculate the voltage, finally, we can get same values in both the cases. Performance point of view, same. But the connection and the elements point of view, these two circuits are not same. Yes. But point to remember, the source transformation is applicable only for the practical circuits. It is impossible to convert ideal voltage source into equivalent current source, vice versa, since there is a violation of KCL and KVL. There is a concept of, if you take the ideal voltage source, if you take ideal voltage source, what is the resistance? 0. Then if you converting into current source means V by 0, infinity. Infinity means that is meaningless. No, you don't have any, practically you don't have any infinite current now. That's the reason why it is impossible to convert ideal voltage source and ideal current source, for ideal voltage source and ideal current source. Source transformation, not possible. Because there is a violation of KCL and KVL. This I given. It is impossible to convert ideal voltage source into its equivalent current source and vice versa. Current source to voltage source, not, since the violation of KCL and KVL. But the source transformation is applicable to even dependent sources also. What are the dependent sources? What are the independent sources? I already explained. For dependent sources also you have to apply, independent sources also you have to apply. But during applying the source transformation for dependent sources, whatever the control variable is present, we know that current controlled voltage source, voltage controlled current, there is a control variable, control parameter in the dependent sources. The control variable must be outside the branch where the source transformation is applied. It is not present in the same branch. This idea. Source transformation is applicable to even dependent sources also, provided the control variables outside the branches where source transformation is applied. So, for example, let this is a dependent source. This is a dependent source, plus minus, and let this is the 10i1. Let this is the resistance 20 volts, and this is the RL. RL is the load. This is RS. And now, what is the source? This is the control variable. Current to controlled voltage source. This is voltage source, but which is the variable here? Current is the control. Control parameter is current control voltage. This I1, here I am applying the source transformation. If you apply the source transformation here, this I1 not present in this branch. Where we are applying the source transformation, at that branch, this will not present. I1 is not present. It must be outside of this branch. Let I1 is present here. This control parameter. Let this is the 40 ohms. And let this is the 50 volts. This is the independent source, 50 volts. Then we can apply source transformation for this one. Because the control parameter, the control variable is outside the branch where source transformation is. Here I am applying the source transformation, but it is outside the branch. Then you can see in the problems how you can apply this source transformation for dependent sources also. Later we will see in the problems. But this point you have to. That is, source transformation is applicable to even dependent sources also, provided that the controlled variables outside the branches. Control variables are outside the branches where source transformation is applied. Yeah, this is the source transformation technique. Then one more topic with respect to fundamentals is that you have to concentrate what the concept of short circuits and open circuits in series circuits and parallel circuits. This knowledge is also very important to solve the different models of questions. All these are the fundamentals that you have to concentrate. Students, up to now, any doubt? So for example, let's consider to explain short circuit, open circuit of series circuits and parallel circuits. Let's consider this is 12 volts, it's 12 volts, and this is current I, and this is 1 ohm, this is 2 ohms, and this is 3 ohms. This 1 ohm, 2 ohms, 3 ohms. Then you have to calculate I. Do this. 7. Yes. It's very simple. I equal to 12 I, 1 plus 2 plus 3. This is how much you can get? 2 amperes. Please, somebody making noise. This is 2 amperes. Say for example, if 3 ohms is short circuit. This is 1 ohm, 2 ohm, 3 ohms. This 1 ohm, 2 ohm, 3 ohm. Now this 3 ohm element is short circuit. Now what are the current streams? Same 12 volts. Now in this case, what the current? I equal to. This is short circuited means don't consider the 3 ohm resistor. This is 12 by 1 plus 2, 3, 12 by 3. Okay, this is how much? Somebody making noise. Please go. This is 4 amperes. For example, 2 ohms and 3 ohms is short circuit. If 2 ohm and 3 ohm is short circuit, this is short circuit. Then what are the current streams? Okay, this is 1 ohm, this is 2 ohms, and this is 3 ohms. This 1 ohm, 2 ohm, 3. And this is 12 ohms. And this is the short circuited lines. Now what are the current? I equal to 12 by. Don't consider 2 ohm and 3 ohm. 12 by 1. That is equal to 12 amperes. Total it is short circuited. This is 12 volts. This is 1 ohm. This is 2 ohms. And this is 3 ohms. It is completely it is a short circuit. Then what is short circuit current? 12 by. Ideally infinity. This is ideal case. Practically very high current. Therefore, in short circuit condition, in short circuit condition, in short circuit conditions, practically the currents are very high. The currents are very high. Ideally infinity means practically the currents are very high. This is the reason. In short circuit condition, why the current is very high. See, that means here 2 amperes, slowly current is increasing 4 amperes, 12 amperes. But this wire is having some resistance, no doubt at all. That's why ideally it is infinity, practically it is a very high. That is, if series branches are short circuited, these are the series branches. If series branches are under short circuit condition, what is the observation? Next, we have to see what are the open circuits in series connection. Let's consider series circuits. Next, open circuits in series circuits. Open circuit in series circuits. Yes. So for example, let's consider this is the voltage source V. This R1, R2 are the two resistors. This is R1 and this is R. Let this is connected like this. The voltage across R1 is VR1, voltage across R2 is VR2. And this is R1, voltage is VR1. This is R2, voltage is VR. Then what the resultant V equals, friends? VR1 plus VR. V equal to VR1 plus VR. What is VR1? VR1 equal to I into R1. Let this current is I. What is VR2 equal to I into R? If it is open circuited, if open circuit, if open circuit, if it is open circuited like this is R1 and this is R2 and this is open circuit. V was open circuit. This is V. Now, what the current in the circuit? I equal to 0. If I equal to 0, what is VR1? 0. What is VR2? 0. But what is open circuit voltage? The open circuit voltage equal to V. That is VOC equal to V. This is the observation. Okay, this is observation for series circuits. Let's consider the parallel connections. That is short circuit in parallel connections. Short circuit in parallel connection. Short circuit in parallel connections. So for example, let's consider this is voltage source. This is R1 and this is R2 and this is R3. This is R1, R2, R3 is the three parallel resistance. If there is any short circuit is provided like this. This is IS. Let this current is I1, this current is I2, and this current is I3. Tell us, what is I1? Can anybody? This is short circuit. What is I1 here? I1 equal to 0. What is I2? I2 also 0. What about I3? I3 also 0. It's completely short circuit. These three elements are shorted. The total current is flowing like this. Then I1 equal to 0, I2 equal to 0, I3 equal to 0. This is one example. See, for example, if the circuit is given like this is the voltage source. And this is one parallel resistance, R1. R1. And let this resistance is R2. Let this is R3. And this is R4. This is R3 and this is R4. These observations are important to solve the different modes of functions. Now it is a short circuit. Let this current is I1. This current is I2. This current is I3. And this current is I4. And this is IS. What about I1, friends? I1 not equal to 0. There is some current through R1 resistor. What about I2? I2 is also not equal to 0. There is a current to R2 resistor. First, this current is divided. Then once enter the current at this point, there is no current through R3, there is no current through R4. The total current is passing through IS, short circuit path. Then what is I3? I3 is also 0. What is I4? I4 is also 0. Clear? Like that we have to. This is about short circuit in parallel connections. Next we will see open circuit in parallel connections. Open circuit in parallel connection. Parallel connection. See, for example, let this is the voltage V. Two resistors are connected in parallel. Let this current is I1. The resistance is R1. This current is I2. The resistance is R. Now in this case, VR1 equal to VR2 equal to V. Parallel connection. If any open circuit is provided, if open circuit, let any one resistance is open circuit. Let this is R1 and this is open circuit. If it is open circuited, what about I1? I1 not equal to 0, but I2 0. But it works normally. It will not damage. It works normally. It works normally. This open circuit voltage equal to voltage across the R1. This open circuit voltage equal to voltage across R1. Clear? That is, there is no current through resistor I2 0, but I1 not equal to 0 because they open circuit. Yeah, these observations are important during solving of the problems. Then one more observation during solving of the problems, friends. To solve the questions, practice questions on elements, to solve the practice questions on elements, this is very important observation. To make this is the note. That is, two elements are said to be in series if the current through two elements is same. That means if any network is given or circuit is given, how to identify the elements are series connection or parallel connection. For that, this observation is important. Two elements are said to be in series if the current through two elements is same. Two elements are said to be in parallel if the voltage across two elements is same. If the voltage across two elements is same, then we can say that those two elements are parallel. If the current through two elements is same, then it is a series. Impedance in series, we can add directly. Admittances in parallel, we can add directly. The impedances in series connection added directly. The admittances in parallel connection, we have to add directly. See, for example, this one. That this is the R1 resistor and this is the R2 resistor. This is R1 and this is R2. Okay. Then these two are in series. These two are connected in series connection. This is series. For example, this is simple. Okay. One more example. Let this is R1 and this is R2 and this is R3. Let this is the voltage source. This is V. But this is open circuit. This is R4 and this is R5. This is open circuit. Now what about observation here, friends? Here if it is a source is connected here, these two are in series. Now current is flowing through these three elements. Because it is open circuit. Once it is open circuit, what the current through this element is 0. The current through this element is 0. Then what about R1, R2, R3? The same current is passing through R1, R2 and R3. Therefore, R1, R2 and R3 in series. These are in series. Because there is no current, once there is no current through R4, this condition is applicable. This is in series if there is no current through R4. If there is no current through R4. For example, I am giving like this. This is R1 and this is R2. This is R3 and this is R4. And source is connected like this. This is R1, this is R2, this is R3, this is R4. Now this is the current. Let this is I, let this current is I1 and this current is I2. Now same current is passing through R3 and R4. Then this R3 and R4 is series. Same current is flowing. This R3 and R4 is series. That is R3 plus R4. This is in parallel with, this current is divided here. Current is divided. This is in parallel with R2. R3, R4 is series in parallel with R2. This total combination is in series with R1. See this difference. Here there is no current. These are in series. But here current is flowing. The current is divided. These two are same current. These are series R3 plus R4 into R2 plus R1. Like this, you have to calculate the R equivalence. Clear. And one more point I told already. If the impedances are in series, for example, this is Z1 and this is Z2. Impedances in series, add the impedances directly. The series impedances are added directly. This is Z1 and this is Z2. Then Z equal to Z1 plus Z2. Admittances in parallel. For example, this is YA. Before starting the problems, these observations are important. That's why I'm explaining. This is Y. Then what is Y equals to? YA plus Y. YA plus Y. Clear? That you have to consider. See, one more example I'm giving here. For example, if the network is like this. Yeah, this is R1. Sorry. That this is R2. That this is R3. And this is R5. R5. Let this is R6. And this is voltage source. This is V2. And this R3, this R4 you have to take. This is R4. Yes. See, for example, let this current is I. This current is I. Take this. This is I. The current is divided. That this is I1 and this is I2. This is I2. Again, this current is divided. That this is I4. This is I3. Then this current is I4 here. Same current. This current is same I4. And this current is I3. What is I3 plus I4? This I2 current only divided. This I2 current I taken as I3 and I4. Same I3 and I4 is entering here. Same I3 and I4 is entering. Then what is current I2? Clear? Now, this is R1, this is R2. This is R3 and this is R. What is the current? What is the current through R3? I2. What is the current through R4 also? I2. The voltage across these two is equal. If it is equal, simply you can replace like this. The same circuit I will draw like this. This is voltage. This is R1 and this is R2. R2. And you have to write this same current is flowing now. This R. What is the current in R3? I2. What is the current in R4? I2. That is R3 and R4 is series because of same connection. R3 and R4 is in series. You have to write. This is R3 and this is R4. You write this R3 and R4 is series. Just simplify the circuit like this. Now, what about this R5? This R6 and V2 is R6 and V2 is series. So, how to draw the network like this? R6 and V2 is series. And this parallel, R5 is parallel. Like this you can draw. See how to simplify the network. Understand, sir? This I taken, this is I. I divided this current is I1, I2. Then this is I2. This I2 is again divided I3, I4. Same I4 is entering here. Same I3 is entering here. The combination of I3 and I4 is I2. That's why I taken this is also I2. What the current through I2? R4. What the current through R3 also I2. Sorry. What the current through R4? I2. What the current through R3 is also I2. Same current is passing through R3 and R4 now. That's why I taken R3 and R4 is series. Then simplification becomes very easy. Clear? Yeah, this observation is also important during simplifying the networks. During simplifying the networks. Okay, this is the concept you have to apply. One more concept before solving the questions, practice questions on the elements. Before solving the practice questions on the elements. Okay, now the time is 7:30. Okay, better to continue in the next class. There is a concept of symmetry in a network. After completing the symmetry in a network, then I will solve some practice questions on the elements. Tomorrow onwards, we'll start some practice questions. After completing some practice questions, then we'll start the nodal analysis and mesh analysis. With that, chapter 1 will be complete. Next two sessions, two sessions maximum. Chapter 1 will be finished. Okay, thank you. This is about the today's session. Any doubt? Please, all of you take this PPT in Telegram channel. Once again, please go through.